Hi, in this video we're going to be learning about De Moivre's theorem. Now, what is De Moivre's theorem? We know that a complex number can be written as z equals to r angle theta. And from this representation, which is in the polar form, if I were to convert it back into the rectangular form, I would write it as r cosine theta plus r j r sine theta. Okay, and we know that this is the real part and this is the imaginary part. Okay, as we can see, the term r is common for both the real and imaginary parts, so we can actually factorize out the r and write it as r z equals to r bracket cosine theta plus j sine theta. And if I were to take a complex number and raise it to a power. Okay, so this is basically how De Moivre's theorem is. When I take a complex number and I raise it to a power, then in this representation over here, I would write it as r cosine theta plus j sine theta, the whole thing raised to the power n. Okay, so the n and n here are the same. Now, how do I apply this power to this representation of the complex number? So it can now be written as Zn equals to Rn cosine n theta plus j sine n theta. Okay, and that is basically your De Moivre's theorem over here. Okay, what do you see here? You see that when I have a complex number raised to a particular power, it is the same as taking the representation of the complex number in this form and just taking r to the power of n, and for cos theta and sine theta you multiply theta by n. Okay, so now let's see how we can actually apply this, or how it is actually very useful for us. Now let's look at the example. Let's say we are given this complex number z equals to 1 plus I root 3. Okay, and I ask you to find z square. What would we do? Okay, we would take z multiplied by z, correct? So that would be z multiplied by z, and it would be written as 1 plus I root 3 multiplied by 1 plus I root 3. So this shouldn't be much of a problem, correct? Because we know how to do the expansion and get the answer. Okay, but what if right now instead of z square I change it to z cube? Then what would we do? We would have to multiply by z, and then over here multiply again one more time. It's still possible, but it gets a bit more tedious. Okay, imagine I raise this to an even higher power, to a power of 7. Then you see that I have to do this multiple times. Okay, and then it becomes very uh, impractical to do it in such a manner. So that is where the De Moivre's theorem comes in very handy. So the first thing is we need to find r and theta. So we are effectively converting the rectangular form representation to the polar form. So let's do that first. So r is equals to square root of 1 square plus square root 3 square, which is square root of 1 plus 3 square root of 4, which is 2. And theta would be written as inverse tangent of root 3 over 1, which is 60 degrees. Okay, so right now we can say that this complex number over here alright, can now be represented using this r and theta. So simply put, it could be written as 260 degrees, angle 60 degrees, which would be represented in the form of 2 cosine 60 degrees plus j sine 60 degrees. Okay, so that is actually your z, which is equals to 1 plus I root 3. Okay, now if I were to ask you to find z cube, okay, all I need to do is, so this is the same as writing 1 plus I root 3 to the power of 3, and that is equivalent to writing it as 2 cosine 60 degrees over here plus j sine 60 degrees over here, and the whole thing to the power of 3. Okay, so looking back at De Moivre's theorem, we can see that once the whole thing is raised to a power n, it is the same as taking Rn and n multiplied by the theta for both cosine and sine. So that is what we are going to do now. So this is written as 2 cube, okay, cosine 3 times 60 degrees plus j sine 3 times 60 degrees, okay, equals to 8 cosine 180 degrees plus j sine 180 degrees. Okay, so when you use your calculator, you can get the answer as 8 into minus 1 plus j0. So the final answer here is minus 8. Okay, so that is how we can apply De Moivre's theorem when you have a complex number raised to a power. Okay, let's look at another example now. Okay, so this question, the complex number is given as minus root 2 over 2 plus j root 2 over 2 to the power of 8. Okay, as what we have seen earlier, the first step is we need to find r and theta. Okay, so let's do that first. So the r is given as square root of root 2 over 2 square plus root 2 over 2 square. Okay, so this is a minus here, and the angle is given as inverse tangent of root 2 over 2 divided by minus root 2 over 2. Okay, so over here for the square root you have half plus half. Okay, because square root 2 over 2 whole square would be 2 over 4, which is half. Okay, and over at the angle side you have inverse tangent of, so these are both the same number, square root 2 over 2 divided by square root 2 over 2, except there's a minus sign, so you have a minus 1 over here. Okay, when you proceed, you get half plus half is 1, square root of 1 is 1, angle of minus 45 degrees. Okay, so whenever you have a negative angle from our earlier videos, you know that you need to draw the complex plane and see where it lies in. So this is negative root 2, so the real part is negative and the imaginary part is positive, so we know that it lies somewhere here. Okay, so the theta, this negative 45 degrees is this angle over here, and the angle that you want to find is this angle. So this angle here is 180 degrees minus 45 degrees, which is equals to 135 degrees. Okay, so over here what you get is 1 angle 135 degrees. So right now I can write it in the form that is suitable for De Moivre's theorem, which is 1 cosine 135 degrees plus j sine 135 degrees. Okay, so since the r is a 1, we don't need to keep writing it all the time. Okay, but just to make sure that you understand what we are doing, I'm writing it. So right now we have converted the complex number into its representation over here. With that, you can actually proceed to find the final answer. So root 2 over 2 plus j root 2 over 2 to the power of 8 is given as 1 cosine 135 degrees plus j sine 135 degrees. Okay, the whole thing to the power of 8. Okay, so now applying the De Moivre's theorem, what we're going to get is 1 to the power of 8 cosine 135 degrees times 8 plus j sine 135 degrees times 8. That will be equals to, so 1 to the power 8 is 1, so we don't need to keep writing that. So cosine 1080 degrees, that is 135 times 8 plus j sine 1080 degrees. So what you'll get is 1 plus j 0, and the final answer here is 1. Okay, so this is another example that we just saw, or how we can apply the De Moivre's theorem to get the answer when you have a complex number raised to a power. Now, another application is finding the nth root of a complex number. Okay, so that is another application area for the De Moivre's theorem. Okay, so that is what we're going to learn now. Nth root of a complex number. Okay, so that is what we are going to find. Now, given a complex number, b is equals to a plus bi, okay, and we are told that this complex number, okay, that means a complex number v equals to a plus bi is an nth root of z. So z is the actual number, and this complex number is the nth root of z. Okay, so that implies that v raised to the n will be equals to z, where z itself can also be represented in the form of r cos theta plus I sine theta. Okay, so with that, okay, we can actually come up with n distinct roots. Okay, we can come up with n distinct roots which are represented as, okay, r root n cosine theta plus 2 pi k over n plus j sine theta plus 2 pi k over n. Okay, so this is the other application of De Moivre's theorem. Okay, the best way to, of course, see how it works is to apply it to a problem and solve it. So that's what we're going to do now. Okay, so the question that we are going to solve now is this: find the fourth roots of z is equals to 5 cosine pi over 3 plus j sine pi over 3. Okay, so what we can say now is, since they have asked us to find the fourth roots, so n is equals to 4. Okay, and when n is equals to 4, that means the values of k, that we're going to use here will go from 0, 1, 2, and 3. Okay, now another thing to note is the pi that is seen here, that okay, represents 180 degrees. Okay, so in your calculator, if you are going to use radian mode, then you can treat pi as it is. But if you're going to use it in degree mode, then you need to make sure that you look at pi as 180 degrees when you are solving the question. So it depends on the mode of your calculator. Now, to find the fourth roots, what we're going to do is we're going to take this and now represent it in this form over here. Okay, and as you can see, the answer, you have four answers because the fourth roots, k equals to 0, 1, 2, and 3. Okay, so let's start off with k is equals to 0. So over here we have r is 5 to the root of 4, followed by cosine, and the angle theta is over here, this theta. So that is what we're going to write here, pi over 3 plus 2 pi k. 2 pi k. What is k? K is 0. Divided by n, and n is 4. Okay, plus j sine, okay, again the same angle, pi over 3 plus 2 pi 0 divided by 4. Okay, so that is the first root that we're going to find. And moving forward, what do we have? So we have 5 root 4. Okay, so let's go ahead and solve this. So over here what we have is cosine pi over 3, okay, divided by 4. So it is times 1 over 4, okay, plus j sine pi over 3 times 1 over 4. Okay, so that is what we have. Now as a next step, we can combine this together. So 5 root 4, so cosine pi over 12 plus j sine pi over 12. So that is the first root, okay, for k equals to 0. Now we can go on to solve for the second root when k is equals to 1. Okay, so let's do that. When k is equals to 1, what we will have is 5 root 4 cosine pi over 3 plus 2 pi k, which is 1, divided by n, which is 4, plus j sine, so the angle is the same, pi over 3 plus 2 pi 1 divided by 4, okay, equals to 5 root 4 cosine pi over 12 plus 2 pi over 4, okay, plus j sine pi over 12 plus 2 pi over 4, and finally we have 5 root 4 cosine 7 pi over 12 plus j sine 7 pi over 12. Okay, so that is the answer for k is equals to 1. So as you can see, the first step is the most important, where you need to make sure you get the r and the theta, all of that correctly. In this question, r and theta are already given. Okay, so all you need to do is apply the nth root formula correctly by looking at what is the n value and the k values for each step. Okay, now let's look at k is equals to 2. Okay, so when k is equals to 2, what do we get? We get z3. Okay, so you get 5 root 4. Okay, and cosine pi over 3 plus 2 pi k over 4 plus j sine pi over 3 plus 2 pi k over 4. Okay, equals to 5 root 4 cosine pi over 12 plus pi plus j sine pi over 12 plus pi. Okay, and the last step would be 5 root 4 cosine 3 pi over 12 plus j sine 3 pi over 12. Okay, now let's look at the last root. So this is k is equals to 3. So you get 5 root 4. Okay, so let me just note this as the answer over here just now. Okay, so coming back to here, cosine pi over 3 plus 2 pi to k, which is 3, over n, which is 4, plus j sine pi over 3 plus 2 pi 3 over 4 equals to 5 root 4 cosine pi over 12 plus 6 pi over 4 plus j sine pi over 12 plus 6 pi over 4. Okay, and finally what you get is 5 root 4 cosine 19 pi over 12 plus j sine 19 pi over 12. Okay, so that is the final answer here. Okay, so the four roots, okay, you can also write them as z1. Okay, so you can call this z1, okay, z2, okay, z3, and finally z4. Okay, so these are the four roots, okay, of this complex number given there. Now let's look at another example. So in this example, we are given the complex number that as z equals to minus 8 plus 8 root 3i, and we are asked to find the fourth roots of z. Okay, the fourth roots of z. So in this question, we first need to convert this to its polar form. That means you need to find r and theta. So let's do that first. So what you have is minus 8 square plus 8 root 3 square, and the angle is inverse tangent of 8 root 3 divided by negative 8. Okay, so what you will get here is 64 plus 192 angle inverse tangent of negative root 3. Okay, and that will give us 16 over here and an angle of negative 60 degrees. Okay, whenever we have a negative angle, what we need to do is we need to draw the complex plane, and as you can see, the real part here is a negative, whereas the imaginary part is positive. So the vector, complex number vector, will be somewhere like or something like this. So the negative 60 degrees is this angle, and the angle that you want to find is this angle here. So it will be 180 degrees minus 60 degrees, which is 120 degrees. So over here, the final answer for the conversion is 16 angle 120 degrees. Okay, now that we have this, we can proceed to uh, find the roots. So let's start with the first one. K is equals to 0. So what you get is 16 root 4. Okay, cosine 120 plus 2 pi k over 4. Okay, so n is 4 plus I sine 120 plus 2 pi 0 divided by 4. So that will give us 2 cos 30 degrees plus I sine 30 degrees. And we'll get 2 0.866 plus j 0.5. Okay, and of course when you multiply inside you get 1.732 plus j1. Okay, so that is the first complex root there. Now let's look at the next one for k is equals to 1. So we're going to do the same thing. Root 16 4 cosine 120 plus 2 pi k is 1 divided by n 4 plus I or j, since I'm using j here, j sine 120 plus 2 by 1 over 4. Okay, so I get 2 cosine 120 degrees plus j sine 120 degrees, which is equals to 2 to the power of, not power, sorry, 2 bracket negative half plus j 0.866, and the final answer would be minus 1 plus j 1.732. Okay, so that is for k is equals to 1. Let's go on for k is equals to 2. So k is equals to 2. Let's do the same thing. So square root 16 to the power, square root 16 to root 4, and then cosine 120 degrees plus 2 pi, k is 2 over 4, plus j sine 120 degrees plus 2 pi 2 over 4. Okay, next we have 2 cosine 210 degrees plus j sine 210 degrees, and next we'll have negative 0.866 here, negative j 0.5, and you'll get negative 1.732 minus j1. Okay, and for the last part here, k is equals to 3. K is equals to 3. What you get is 16 4 cosine 120 degrees plus 2 pi 3 divided by 4 plus j sine 120 degrees plus 2 pi 3 over 4. Okay, then you get 2 cosine 300 degrees plus j sine 300 degrees. Okay, and you get 2 0.5 minus j 0.866. Okay, and finally the answer will be 1 minus j 1.732. Okay, so as you can see, it is the same steps again and again. Okay, except that you need to be very careful about making sure you get the r and theta correct first, and subsequently you can just apply them to the finding of the roots. Okay, so let's just do one more example, okay, for this lesson here. The question we're going to be looking at now is that we're supposed to find the cube roots of -1 and plot them. Okay, now let's look at this number -1. So when I write z is equals to -1, what do we see? We see that this has only the real part, correct? There is no imaginary part to it, okay? Which means that if I were to actually draw it on the complex plane, okay? If I were to actually draw it on the complex plane, it will actually be over here, -1, okay? But to make your analysis a bit easier to understand, you can always write it as z equals to -1 plus j0. Okay, so in this representation, you can see that you have a real part and imaginary part, and maybe writing it this way could actually help you to follow through the steps as how we have learned. Okay, so let's go ahead to analyze this first. So from the xy plane, we know that the uh, complex number is actually just a real number over here. So the angle that we expect is 180 degrees, and the R value would be 1 because it is only absolute value of 1 over here. But if we were to go ahead and do it step by step, okay, we can also see that you will get square root of -1 square plus 0 square. So we're trying to find the R and the theta here. Inverse tangent of 0 over -1. So you'll get this is equals to 1 angle 0 degrees. Okay. Now, if I were to uh, see that this is 0 degrees, which is what your calculator would give you. Okay. But at the same time, okay, you can see that because of our understanding that this is actually on the negative part of the real axis, the angle should actually be written as 1 angle 180 degrees. Okay, so this is the important thing we must understand. Okay, when you just have a real number or a or imaginary number, okay, when you are trying to get the angle, do draw it out on the complex plane and then see for yourself where the angle is supposed to be. Okay, so since we asked to find the cube roots, we can start off with when k is equals to 0. So we will have, so since r is equals to 1, we don't need to keep on writing r. So we can straight away go into the angles. So cosine of 180 degrees plus 2 pi 0 over 3 plus j sine 180 degrees plus 2 pi 0 over 3 equals to cosine 60 degrees plus j sine 60 degrees equals to 0.5 plus j 0.433. Okay, so that is for k is equals to 0. Now for the next one, we have k is equals to 1. So we'll do the same thing, cosine 180 degrees plus 2 pi 1 over 3. Okay, so in this case n is 3, right, because we are trying to find the cube roots of it, plus j sine 180 degrees plus 2 pi 1 over 3, and that will give you cosine of 180 degrees plus j sine 180 degrees equals to -1. So that is your second root, and the third root here, okay, k is equals to 3. So what we will have is k is equals to 2 over here, and what you will have is cosine 180 degrees plus 2 pi 2 over 3 plus j sine 180 degrees plus 2 pi 2 over 3 equals to cosine 300 degrees plus j sine 300 degrees, and that would give you answer of 0.5 minus j 0.866. Okay, so these are the three roots. Okay, and we are asked to plot them out, so let's do that. Okay, so you have your, let me draw it a bit neater. Okay, so you have your real part and your real axis and imaginary axis. So the first one is real is positive and imaginary is also positive. Okay, so it will be somewhere here. Okay, so that is your first root. The second one is -1, so that is what we have here, -1. And the last one is 0.5 negative j 0.86, so it will be somewhere here. Okay, so this is how the plot of the three roots will look like. Alright, so I hope that this video, okay, has given you a good idea on how we can actually apply De Moivre's theorem, okay, to solving complex number related problems. Okay, so thank you once again for watching this video, and I'll see you in the next lesson. Thank you. Bye.